I will show you live how seamlessly you can create a Kubernetes cluster, in fact a managed one using Camphor Multicloud Gateway software. Okay, so for this demo I am going to use this picture for throughout this video. Okay, so this is going to be basically a Kubernetes network cluster creation. Okay, the way I will do it is obviously using a lot of automation. That's my only helper. So I'm going to start the script which will kind of do everything, and then I'll walk through as it runs in the background. So I'll start it right now. Okay, so that's starting. Now let's go back to the picture. So what are we talking about here? Today we are going to talk about EKS, Elastic Kubernetes Service, which is basically a managed Kubernetes service provided by AWS, wherein Amazon will basically manage the control plane of the Kubernetes. They'll give you HA, they'll give you all the configuration, they'll back up all the configuration of the Kubernetes and whatnot, the etcd database, if you will. And let users focus on their use case, the business cases, by managing the workloads of Kubernetes on the worker nodes, which are the compute nodes. Okay, and those are the compute nodes which will be like, just like any other EC2 instances that you typically pick. Right, that's how the EKS has been architected. What we'll do in this demo is that we're going to do exactly that. We're going to use Terraform, which is for like a declarative way of configuring cloud resources, including the EKS. We're going to use that to create these cloud resources, and what we'll do is using the cool Camphor Multicloud software, we are going to create like a one-on-one mapping between the worker nodes of the Kubernetes, which will be running on AWS, with an on-premise node as well. So we'll have one native instance, like a native worker node, and we'll have three worker nodes. You can call them as a dummy worker node, but they're just like any other worker node, except that they'll be one-on-one mapped to an on-premise instance, which could be a bare metal or it could be a virtual machine. And all the traffic that hits the proxy instance one here will actually go to Camphor instance one, and vice versa. Same thing with 2 and 3. Now, what is the advantage? Advantage is that basically because your actual containers will be running in these on-premise instances, you can add as many CPUs and memories and GPUs and storage and whatnot seamlessly, yet utilizing the complete cloud-based workflow cycles. Okay, so that's the main proposition with this design. Okay, so now let's take a look what's happening. So it is now creating the EKS cluster. So I will quickly walk through like sort of what are the key variables. So using Terraform, I'm doing all this, and there's also auto scaling group and all those fancy things. Okay, so let's look at the AWS side. So here is the input to the AWS Terraform input file. So region is ES Houston, Ohio. There's some credentials and whatnot. I think there's not much here. Actually, the only thing you have to say is, okay, what is the VPCs and the type of the instances. Okay, so this is important, right? You don't need large instances, which is what you typically need to run your compute workloads. You can use as small as possible, just enough to encrypt the data, send it across the internet. So I'm going to use a micro instance, which has I think just half a gig or 1 gig of memory, just one vCPU, right? You can't do much out, you can't run anything, but I'm going to actually run a e-commerce web application on premise and showcase how it is seamlessly integrated with the EKS. Okay, that's that. And then on the on-premise side, in order to create the virtual machines, I'm going to use OpenStack. Okay, you can use the VMware vCenter, libvirt, Docker, Camphor Cloud. We have our own software to manage VMs. You can use that as well. And here is like OpenStack information, and I'm trying to provide like how much CPU memory and all you want, which is now fully under your control. Okay, so that's what this is, right? And then there's some network ports and other things. Probably like what is the name of the cluster and the version. In this case, I'm going to pick 1.29. Number of instances is Camphor is going to be 3, and the regular instance, meaning the regular worker node, which is not going to have a corresponding counterpart in the Camphor cloud in on-premise. So that's just 1. So we have totally 4 compute nodes, right? Now what the script will do, the script is trying to basically create a cluster, and then it will bring up the worker nodes. It will bring up the corresponding worker nodes in the OpenStack. It will make sure that they can communicate properly. And a whole bunch of things happens, frankly. I still expect the entire demo to be complete under 30 minutes. The biggest bottleneck actually is the creation of the cluster itself, which is on the Amazon side, not on the Camphor side. Okay. While that happens, let's look at the architecture a little bit more. Okay. So what's happening here, right? So there are these three instances which will be created as worker nodes in AWS using T3.micro, very small. You can't do much realistically, and they will be connected to a cloud gateway. And in this case, we'll have just one network because this is a simple case. You don't need multi NICs and all that, so it's going to have just one network. Each of these instances will be sitting, I think, 122.25.0.0/24 network, if I remember right, and they'll be connected over internet to these on-premise instances created by OpenStack. There's going to be this cool optimized internal network. If you had followed my previous video, this will be familiar. Basically, what this is if you look at the path between these on-premise instances, in order to reach from compute, let's say Camphor instance 1 to Camphor instance 2, there are two paths. One, you can go to the proxy instance in the cloud and then go to cloud gateway and then come back to proxy instance. Don't come to here, right? That's one part which goes over the internet. So there's two issues. One, there's a higher latency, obviously, because you have to go all the way over the internet and then come back. Second is the egress cost. Every time you send data towards the cloud, there's going to be a billing associated with it. Both are unnecessary, right? Because you're running on-premise, obviously you will have your own connectivity internally. So what Camphor can do is it can create a secure, seamless overlay SDN based network on top of your corporate network or whatever optimized network you have, and it's going to create this optimized network. So any package sent from here destined to Camphor network will actually go through a local overlay network. It will not go through the internet. Okay, so that's the cool part. I have already showed you demo this. If you're interested more, you can look at my previous video on the service chain. The same technology will be used here as well. Okay. Once the Kubernetes comes up and once all the worker nodes register with the Kubernetes control plane and all that, we will go through the EKS control plane. We look at how EKS looks at all these things. Okay, and then we'll also deploy an application. Actually, we're going to pick a e-commerce application called Sock Shop, where you can purchase socks, including smelly ones. Interesting, right? So anyway, so we will deploy a web application whose pods will be distributed across these four worker nodes. But here, because these are proxy instances, the actual containers will be running in the on-premise instances. So if you were to, let's say, have a database on-premise and need access, then you will have ready access from this system. That's why it is, multi-cloud networking is what it is. And then, of course, if your container could be running in these instances also, which is like a regular worker nodes, but they will have seamless communication to the other worker nodes over this internet secure tunnel set up by Camphor networks. Okay, anyway, just keep an eye on what's going on here. Still, the cluster is being created, and it almost takes 5 to 8 minutes actually. That's what I've noticed. In the meanwhile, let's look at the cluster itself. Okay, so let's open the tab for EKS. So this is my Amazon dashboard, AWS dashboard to be precise. And this is the Kubernetes that's happening. As you can see, there is a cluster being created. Camphor cluster EKS is the name of this, and its version is 1.29. Okay, so it's getting created. It usually takes around 10 to 15 minutes to get fully created, and then once it happens, then the worker nodes will start registering with it and all that will happen. Okay, and then you will actually start to see the worker. Right now there's no worker node. If you look at this, there's no worker node at all. That's why there's no worker node in the OpenStack also. Let's look at the OpenStack dashboard in the meanwhile, how it looks. Here's my OpenStack dashboard. I've created multiple projects, so let's pick the EKS one and create the instances. There's no instance right now because nothing has been created. The design is, at least in this particular example, every time, let's say you create a new worker node or take away worker node, either way, because that's kind of tied to an auto-scaling group. Then if you keep running that software, what happens is the Terraform will contact OpenStack and will create a corresponding on-premise version. Okay, so if this one goes away, then this one goes away. If this one comes, a new one comes in, a new one will come in. So that's how you can kind of tie them together to almost get the feel of an auto-scaling group, pretty much working right away on the on-premise side as well. You can also make that static if that's auto-scaling is too complex, but that's more to be learned there. But at least you will in this video, by the end of the video, you will hopefully you'll be able to see and appreciate the value that this really cool technology brings to the table. Okay. And as we were saying, we're going to deploy this application, right? So one of the cool thing about Kubernetes is that a lot of deployment constructs are natively supported with the well-known clouds. Okay, one of them example is a load balancer, right? So typically when you want to deploy an application, you want to attract traffic and you want to balance it, so you want a load balancer. So in Kubernetes, there's something called service, and in a service type, you can, if you specify it as a load balancer, and if you are running on the cloud, you get a ready integration with the cloud counterpart, like cloud gateway in this example, or cloud load balancer in this example. That all will continue to work seamlessly in this design, guys. I mean, that's the beauty. Okay, so meaning when in these on-premise instances you deploy a Kubernetes service and that Kubernetes service says I want a load balancer, it will actually realize it's running in AWS, because for all practical purpose it's running in AWS, from a networking perspective. So it realizes it's running in AWS, so it's going to contact the AWS gateways, API gateways. It's going to create the load balance for you. It's going to come do the complete management of the cycle of that load balancer and whatnot. And the end result is you will get a clean load balancer which you can access to get to your e-commerce application in this example. So pretty much everything happens exactly like as if you were running EKS with worker nodes running natively in the cloud. Exactly same will happen, except that you have the flexibility of choosing some of the worker nodes to be on-premise, some of them not, based on your compute resource availability and requirements, like a supply and demand. So based on that, you get the full flexibility. And as I said before, for the on-premise worker nodes, you don't have to pay on a per hardware basis. You don't have to pay extra money to the cloud for more CPUs, more memory, and more GPUs, right? Certainly. So if you have your own GPUs that you can purchase or you can get it from your third party, feel free to do that. And you can, in fact, if you use OpenStack, you can even manage the flavors and all very well. So you pretty much get what I call is as an on-premise based cloud deployment. This is like Outpost from AWS, if you will, but the budget, the pricing of Outpost is over the chart. Okay, so it's completely over the roof. This is a very different. You continue to pay using your regular pay. These microinstances will cost you, like, believe it or not, $5 a month or something like that. Just throwaway price, right? And of course, if you have more data going across north south, then you may have to add more CPUs to these cloud instances, and if you don't, then you don't. So that's the part. And at the same time, you also have the luxury to keep scaling on the cloud also, meaning you can also have these cloud instances uh, supporting your scalability. So if you don't have enough resources on the on-premise, or let's say if your on-premise data center goes down, you can have a design wherein your auto-scaling group can launch more instances cloud native, and that way your application can continue to work seamlessly. Okay, all the configuration, everything typically is managed by the control plane, and that will be managed by EKS, okay, which has a flat fee of around $75 per month. That's the quoted price. I guess with the discount, you can probably get even maybe 50 or below. Okay, let's take a look at what's going on here. Okay, so looks like the cluster itself is up. Now we are trying to reach the expected computes. So as I said, we had supposed to have four, right? So three of these guys and one of this guy. So this one has already come up. We can take a look at it actually and see what it thinks. So if I click on this cluster now, and if you look at the compute, I think the managed node groups is still being created. So there are some authentications that has to happen. There's some access profiles that is set up. So that's why you don't see any computes right now from a Kubernetes perspective. Actually, now you do, right? You will see it here. So there's one compute now which is ready now, okay, which is the native instance, actually 0.41. So if you look at here, let's look at VMs on the AWS side. See, there are 4 machines created. This one should be the 41. Yeah, see here, 172.25.0.41. This one is up and ready and already registered. Other 3 guys have not. Why? Because these are dummy instances. We need to have corresponding OpenStack ones. So let's see if the OpenStack is there. Maybe not yet, I think. Oh, okay. So the instances at least have been created just 3 minutes ago. So there's 3 instances created on-premise in OpenStack, and these 3 will correspond to these 3 instances on the cloud. And what is supposed to happen, fingers crossed, is that those three instances will come up, and then let me show you actually a little bit more on the code side. Those the OpenStack instances have some cloud init configuration. Okay, simple one. I can show you here. This file. It's a Jinja template, but don't worry about it. Just a little bit of code in the YAML file, but it's not much. But basically, it's injecting the necessary private keys for authentication, so it can talk to the public instance or securely. And then it's going to run this Docker command. Okay, it's basically going to install some prerequisite software, load the image, and then just run it. What it does is, here is the key part: set up EKS node. So it's going to set up the multi-cloud gateway networking, and then it's also going to set up the EKS part, meaning it's going to make that on-premise node, this particular instance, as an EKS Elastic Kubernetes node compute instance. So it's going to go securely talk to the control plane, get registered and everything. Okay, lot of things here. I mean, really, really cool stuff. Hopefully, it excites you as much as it does to me all the time. Every time I look at it, I can't believe actually it works, but it does. And let's see. This is a live demo. I'm trying to record. So hopefully there won't be any hiccup. Maybe the demo gods be with me. Okay, so let's see what's going on here. Still, the compute nodes is just one, and the reason is there's going to be some initial software installation that has to happen. There's a bunch of apt-get that has to happen, and because I run my tests so often, Ubuntu continuously throttles my home lab network. So that's why sometimes the installation can be a little bit slow, but I don't expect this to be in any production deployment at all. So if you have a good internet connection without any throttling, you can get this ready in under a minute or so. But right now it's going to poll every minute. I let it continue and continue with the discussion on the architecture. Okay, so here, remember, this Kubernetes control plane will not talk to a worker node actually, unless the communication is fully secure, authenticated, and the handshaking happens as it is expected to. Okay, and the reason why this should work here is because the data that is coming from this instance is all fully secure, and it is using exactly the same keys that a valid worker node is supposed to use. So there is nothing that's happening out of the sort of out of the normal work cycle, right? That's why Kubernetes control plane should be eventually happy to accept the request from these guys, which is actually come from here, and honor those requests, right? And then the second plane is the data plane. I mean, the Kubernetes has two parts. There's a control plane and then there is a data plane. Okay, data plane is equally important, or maybe even more so, actually, compared to the control plane, because when the containers eventually gets launched on these worker nodes, they should communicate, right? The east-west communication that will be happening through something called CNI, which is what is it? Container network interface, I believe, right? So that's the sort of a networking plugin architecture in the Kubernetes, similar to, if you're familiar with OpenStack, similar to the Neutron networking architecture in the OpenStack world. Okay, so that in this example, I am going to use Calico. So AWS provides a flexibility, thankfully, to change it. Because if you were to use the Amazon native VPC as a CNI, which you can, by the way, guys, the only thing is there are so many limitations. Like, for example, you can't have more than 2 or 3 service IPs if the instance type is micro. I mean, so they have these restrictions based on, because I know for whatever reason I don't understand, but they have these restrictions. So because we're using a micro instance, you can only have like 2 or 3 IPs. But if you were to switch it to, let's say, Calico for the CNI part, then you don't need to worry about all that, because the way Calico works is that for the intra subnet, it's just going to use but first of all, it's going to use an overlay, and it has like a new service IP address range that it's going to use, which you can customize also for the inter pod communication. And even there, it will only use overlay if you are going across subnets. So if you're on the same subnet, in this example, all these worker nodes are on the same subnet, you will not, there's no overlay overhead also, because it's just going to be pure routing. It's going to say, okay, for all packets assigned to this 10 dot whatever the cluster IP range, next up is this worker node IP, and because they are in the same subnet, they're reachable. And all of that should continue to work in this architecture also. Why? Because these instances, worker nodes, are sitting in the same subnet actually underneath, an overlay subnet, if you will, based by managed fully by Camphor seamlessly. Okay, So here you can see now we have 2 compute nodes up out of 4. So one has come up. So I expect this count to reach 4 soon, maybe in the next iteration or the one after that. And then we will see. In the meanwhile, let me do a little bit more here. So we're going to run get nodes command. Basically, this is a kubectl command using the context as Camphor. As you can see what's going on. You can see actually 3 of them are up. Just one of them is not up yet. Once this node also comes up, we'll have 4 compute nodes ready, and we'll actually go ahead and deploy an application. Guys, let's do that. But anyway, let's look at what the dashboard things here. The EKS guys, they are happy with 3 guys. The other one has already contracted also few seconds ago. So hopefully the CNI will get set up the Calico, and this should become ready pretty soon. Once that happens, the cluster is ready, and once the cluster is ready, we'll go ahead and deploy the application. Okay, so let's wait for that. Meanwhile, I'll continue what I was discussing, going back to the picture. So here, so I have these 3, I think 2 of the 3 are up. This one is up way while ago, and they should be able to talk. Maybe we should go ahead inside one and take a look, right? Why not? We should definitely look at it. So let's look at which one? This one, right? 0159. Let's see what is 0159. I think the way, because it's an auto scaling group, there's no numbering here 1, 2, and 3. So we will just pick one and see what happens. I don't think it matters. On the on-premise side, I do have the names. So let's look at this one, 219. Okay, just quickly check if it's up. Okay, it's up. So now it should be 4 next time. Okay, guys. So now what we will do is we will log into one of these machines using OpenStack floating IP. Okay. You can also use public IP of the instance. So here it is, right? Now I look at the routing table here. So in this example, because it's EKS, this is a complete cloud mimic. Okay, so including the default route. Look at this here. The default route. First of all, let's look at the source address of the interface, the tunnel interface, which is 0159, which is exactly what Amazon Cloud Instance has, right? 172.25.0.159. So it's a DHCP base, and we have that. Let's try to ping the gateway 172.25.0.1. Boom. See, it takes around 90 or 100 milliseconds to reach over the internet. Okay, and the default route for this route is actually going through the Amazon gateway. So every single traffic, right, it actually goes to the cloud gateway. So if you have any security group that you have configured, they all will work very well, exactly how it's supposed to, right? So this is pretty much your on-premise instance. So you can see here, I have 2 CPUs and 3 gig of memory. You don't get this with a T3 micro at all, right? So it is running on-premise. So if you have a GPU, you will get a GPU, guys. So that's the power, okay? And you should be able to reach all other instances in a very quick way. Let's look at the optimized part. So let's try to ping another guy's private address. Okay, 34. This should happen within a millisecond or 2. Okay, yeah, there it is, right? Less than a millisecond. Why? Because it's not going to the internet. If it were to go over the internet, I'm here in San Jose, the lab. If it were to go through internet, if you go to Ohio and come back, it's almost 4,000 miles round trip. Speed of light is finite, right? And a constant, supposedly. So it will take almost 15 milliseconds to do that. So as you can see here, obviously it's happening under a millisecond implies that it's definitely not going over the internet at all. Just the physics will tell that. I don't need to verify in any other way. Okay. So the optimization is working. Now let's say if I ping the native worker node, okay, for which there's no counterpart in on-premise, right? So what is that? That is this guy, okay, without Camphor in the name. So that's 41. So let's ping that, and that should go over the internet. And you can see the the latency. So the round trip time is 85 milliseconds, right? So everything is working so far, so good. Let's see what's happening here. Beautiful. So now we are actually deploying the application. Okay, I'll show you the application also. What we are deploying. So the application we are deploying is something called Sock Shop. Okay. So basically it's an e-commerce web application. This web application is going to deploy a bunch of pods, containers, database, services, as you can see, there's a data RabbitMQ queue. It uses many features of the Kubernetes. If anything were to break, whether the DNS, whether the MTUs, whether the services, the pods, the Docker registry, you name it, right? This demo will fail, for sure, right? So it's like a rocket launching. One minor thing fails, the whole project goes for a toss. So here you can see that the service asks for a load balancer, like I said in the initial part of the demo, and we have gotten a load balancer from the Amazon, guys. Isn't this cool? So the Kubernetes, the EKS deployment is asking for a load balancer. The worker node, though it's on-premise, is thinking it's running in AWS. It contacted the cloud gateway. Cloud gateway is extremely happy because everything is perfect. So it gave it response back successfully and a load balancer has been created. So this is the load balancer which you can use now to access this web application itself. Let's see if the pods are up in this web application. Okay. So this is a socket shop. So they're coming actually. You can see most of them are green. Just a payment gateway when the user is coming up. It will come up soon. What we can do now is that, and the script is also trying to verify. We should be able to do a curl. In fact, we'll go to the browser. We should be able to access this web application. Okay. But before we do that, let's look at what the EKS thinks. Okay. Now again, let's refresh this. I have how many? 4 nodes, guys, right? 4 computers. You can see here, 4 computers. They're all ready. Meaning the worker nodes, even though running on premise, it's able to successfully register with the EKS control plane, and that's why the control plane says that these 4 worker nodes are now ready for deployment. Okay. Now let's look at the resources of this compute. You can see here there's some Calico nodes I was talking about. There is a bunch of I guess deployments. That's what the socket shop does. So you can see here all these deployments was as a part of an application. Okay, they've all been set up and they're all green, right? So we can narrow down to the socket shop application namespace only, and you can see they're all happy and running. One is ready, right? So you can look at anything just like you normally use with your EKS. Here's the pods. The pods have been created. Everything will work exactly like how it's supposed to in a normal EKS setup, except the worker nodes are coming from on-premise. Let's see if the script is completed, guys, which means that this web application is ready. Let's see if it works. Shall we? Let's go here. In fact, I'll go through Amazon only, okay? Because there must be a web application load balancer created. Even Amazon will tell you that there's a load balancer. Let's go from there also, you can see. Or we can just copy paste that URL. See now if you go here, there must be a load balancer created here. You can see there's a load balancer here created. How was it created? It was created through Kubernetes, okay? Kubernetes is running in AWS. At least that's what EKS thinks. And it is happening from a control plane perspective, but the worker nodes are actually coming from on-premise and also cloud. It's a combination, right? A really complete multi-cloud use case. So here is the URL for the load balancer. This is a DNS record. We'll access it. We are supposed to get a e-commerce web application as a result. Okay, let's see how it works. So first, so good. I see some response. I see a title here, WebSocks. Boom. Here's web application. Isn't this cool, guys? So the web application is, let's go back to the load balancer here. I'm using the socket, the port number 80 actually. Okay, so let's look at this load balancer once, what it thinks as far as the worker nodes are concerned. See, all the 4 worker nodes are healthy. So basically, this load balancer now can actually redirect traffic to any of the 4 worker nodes. Okay, any of them. Still, the networking is all set up seamlessly. The traffic should work from. Here is a beautiful thing. Here's a socks shop web application. You can go ahead and buy socks here. And as I told you, this application, here is smelly socks. So if anybody wants smelly socks, you can use this website and buy right away $1 million per socks, guys. Okay, nothing more, nothing less. Okay, so but you can see that for this web application to work through this load balancer URL launched by Kubernetes through AWS gateways, this is just unbelievable. This is ready for deployment. You can see this one, I think, is a groundbreaking technology. I don't believe there's any other company or any other product which can do what Camphor Multicloud Gateway can do. This is as seamless as you possibly can get. Once again, guys, There's 4 instances here. Look at these instances. These are micro instances. I mean, micro instances, nothing. See here, T3 not micro specifications. What do we get out of that? I mean, nothing. I'll show you. So you will get 2 VCP and 1 gig of memory. Okay. But if you look at the instance, that's not what it is. Actually, I'll show you one more thing. Let's look at the Kubernetes, guys. What does the Kubernetes thinks, okay, about the compute nodes capacity? That will itself tell you. So here, so micro, right? It should have what? 2 VCPs and 1 gig of memory, correct? Let's click on it. Is what it thinks it is, Kubernetes. Oops, not really. It's got 2 CPUs and 3 gig of memory. You see, guys, here? Why is 3 gig? Because it's all coming from the on-premise counterpart. Now, you can have 300 gig here. Your cloud bill will still remain the same, except the egress cost of the networking. So as long as your network cost is not humongous, or if you have a flat metered bill where you don't necessarily pay per byte of data egressing, you can use this technology seamlessly. Okay. And now there's a auto scaling group also associated, guys. Here is, I'll show you also. So auto scaling groups. So as part of Terraform deployment, there's an auto scaling group created. Here it is, right? One for on-premise instances, one for the cloud native instances. Now, based on this auto scaling group, if it creates more instances, then we can create more instances in the OpenStack on-premise. If it removes some, we can remove some, right? Everything will look exactly how the design is, it is supposedly designed. Okay, so here it is, Elastic Kubernetes service, okay, working in real time. Now I'll also destroy this demo. Let's show the get pods once again. Okay, everything should be green because it is working on the online. So okay, everything is green, perfect. Okay, and now we'll test. And by the way, look at the total time. Actually, it took 25 minutes. Okay, and out of 25, frankly, the cluster creation from AWS was almost 15 minutes. So there, you can see, right, how cool it is. Now I'm going to destroy this whole thing again, completely automatic, because I don't have an assistant. So computers and automations are my assistant. They will do their job. And now destroy this whole cluster, and I think that will take another 5 minutes. But anyway, I think I've kind of explained to you what I'm talking about. Hopefully, you can appreciate what I'm bringing to the table, what Camphor Multicloud Gateway brings to the table. Seamless, guys. Pure multi-cloud you can do with clear use of on-premise resources and cloud instances. Okay, you can use all the cloud features, well, security groups, IAM policies, S3 bucket storage, IAM load balancers, CloudWatch, EKS index, everything, and from the on-premise directly. So I hope you like it. If you do like it, subscribe, share. I'll put more videos, in the near future with GKE, Azure, your Oracle, So we'll support all the clouds out there who wants to be part of this amazing journey. Please do like, share, and contact me if you want to, take this further. Appreciate it. Bye bye.